Hey guys, this is me Kong again from Posh Coaching Classes. Hope you all are doing fine and you're safe at home. Please do not go out as this is COVID times, right? So today's topic, what I am going to start is for class 10th. This topic is class 10th maths. So this is for the students of class 10th. I am going to start the chapter that is the first chapter, the very beginning of the book. So I will be giving you videos on all the chapters which are there in the book. So as you are at home, you can definitely go through these videos and you can practice them at home, right? So today's chapter is chapter 1, class 10th NCERT, and you can definitely understand a new thing in the very first exercise, that is Euclid's division method. You might have done HCF, highest common factor, using the prime factorization method, but today we will learn another method of HCF, that is highest common factor, using Euclid's division method. So let's get started. I'm going to start with the first question. So before that, this is class 10th, subject is maths, and this is chapter first. Okay, exercise 1.1, right? So I will just write the question. So here's the first question. The first question says, use Euclid's division algorithm to find the HCF of, and then we have three things. So the three things are 135 and 225, then we have 196 and 38220, and the third part is 867 and 255. So we have to find the HCF, but not using the prime factorization method. In case, first of all, if I just let you know about the prime factorization method, in case if you have forgotten, so I'll just let you know about it. So what we used to do, 135, take the factors. So 5, 3, 8, 1, 9, so divisible by 3, 3 4s are 12, then we have 3 into 5, then 3, 1, then 3, 5, then again 3, 5, and then 5, 1. What about this? It is 2, 2, 5. 5, 4, 9 means divisible by 3, 3, 7, 3, 5, 3, 2, 3, 5. Then we have 5 into 5, 5, 1. So then the factors of 135, we had 3 into 3 into 3 into 5, and the factors of 225, we have 3 into 3 into 5 into 5. So you must remember, and you have done it earlier as well. So when we are trying to find HCF, we see what are the common things. Here I can see the common thing is 3, then we have another 3, and then we have a set of 5 as well. So if I multiply 3 multiplied by 3 becomes 9 into 5, so it is 45. So the HCF of 135 and 225, it is 45. So 4, 5, 45 using prime factorization method. This method is prime factorization method. But our question is not about prime factorization method, it is about Euclid's division. So we'll just remember the answer is 45. So I'll just rub this off, and then we will solve it using Euclid's division method, right? So this is done. Now we will use Euclid's division. Now what does Euclid's division say? We'll say using Euclid's division lemma. Lemma or algorithm or theorem, anything will do. You must remember one thing in Euclid's division lemma, that is dividend is equal to divisor into quotient plus remainder. This is the most important thing in Euclid's division lemma. Why? Because we will be using the same set of things, or we will be using the same formula to solve this question. So what we have to do, first of all, if I'm taking the first part, first part is 131 and 225. 135 and 225. So first thing what I need to know is which is the bigger equation. So I know this is the bigger term. So I have to take 225 and divide it with the smaller term. So the smaller term is 135. Now, if I multiply 135 into 2, it becomes 270, which is more than 225. So what I'm going to do, I'll put a 1 here. It is 135. 5 gone means 0. Then we have 12, 9, 10, 11, 12 means 9, and 1 minus 1, finished. So I will say dividend. This thing is known as dividend. So 225 is equal to divisor, which is 135, multiplied by quotient, which is 1, then plus remainder, which is 90. Okay, so this is the first step in the Euclid's division. I hope this is clear to you. What you need to remember is this formula. Dividend is equal to divisor into quotient plus remainder. And then you need to see, if you have two terms, you need to see which is the bigger term. Then you have to divide the bigger term with the smaller term. And you need to continue this thing till the time your remainder is 0. So how to do that? We'll just do it right now. Here we don't have a 0, so we need to go to the next step. So I'll write here, since remainder is not equal to 0, therefore using Euclid's division lemma, now I need to pick up these two things. I have to leave the quotient, then 135 and 90. I will divide again 135 with 90. So 90 multiplied by 2, it is 180, more than 135. So 90 multiplied by 1 is 90. And we have the remainder 45. So I'll write the same thing using the same formula. So 90 is equal, 135 is equal to 90 multiplied by 1 plus 45. Still the 0 is missing. So I'll write again, since remainder is not equal to 0, then again pick these two, 90 and 45. 90 divided by 45, 2. 45 multiplied by 2 is 90. So I will write, using Euclid's division lemma, 90 is equal to 45 multiplied by 2 plus 0. Right? Now I have got the 0. That means I need to stop here. So if you see, what is this? This is 45. So I can say HCF of 135 and 225 will be using Euclid's division is equal to 45. If you remember, doing prime factorization method, we got the same answer, and with the Euclid's division method, we again got the same answer. So the answers will not differ, but the procedure is a different one. So this is Euclid's division. I hope you understood this. The first thing is your formula, that is dividend is equal to divisor into quotient plus remainder. Then find the bigger term and divide it. Just continue the same steps till you get the remainder as 0, and then whatever is here will be your answer. So I hope this is clear. If you want to make a note of this, please pause the video and make a note of this, right? Alright guys, so we are done with the first part. Now we have the second part. It says 196 and 38220. So we will use the same Euclid's division lemma for all the parts, and the same formula will be there, that is dividend is equal to divisor into quotient plus remainder. So I'll take this 196 and 38220. So this is the bigger one. So 38220 divided by 196. So 196 multiplied by 196. 12 minus 6, 6, then we have 17, 10, 11, 12, 13, 14, 15, 16, 17, 3, 3, 6, 8, and then we have 2 minus 1, that is 1, and then we will take this 2 down. Now we'll multiply 196 multiplied by, let's take 9, 9, 6, 54, 9, 9, 81, 86, then we have 9, 1, 10, 11, 12, 13, 14, 15, 16, 17. So it is 9, 1, 7, 6, 4. Then we have 12, 5, 6, 7, 8, 9, 10, 11, 12. So that is 8, 9. This is 0, 0. And then I have 0 here. So 196 multiplied by 5, 6, 30, 9, 5, 9, 45, 48, 980. So this thing exactly gets divided. So we have 195 here, so 980 here, right? So quite easy. So what I will write, I'll write 38220 is equal to 196, that is divisor, into quotient is 195 plus remainder is 0. So this question finishes in the first step itself. Why? Because our thing is that we need to get 0 in the remainder, and that is already there, so we don't need to go further. So therefore HCF of 196 and 38220 is this thing, 196. I hope you understand this as well. If you want to make a note of it, please pause the video and make a note of it. Alright guys, so now the third part and the last part of this question. So the third part is 867 and 255. Okay, so now what we need to do again is see the bigger term. So 867 is the bigger term. We will divide 867 by 255. Let's see, 255 multiplied by 3, 15, 16, 7. So this is the one, so 3, 7, 6, 5. What I get, 7 minus 5, 2, 0, 1. Okay, so using Euclid's division lemma, we can write 867 is equal to divisor 255 into quotient is 3 plus remainder is 102. So this is the first step. You know there is no 0 here, so we need to follow. We need to go further. So here we can write here remainder is not equal to 0. Therefore, using Euclid's division lemma, what do I have to pick? 255 and 102. Let's divide it. 255, 102. 102 multiplied by 3, it will be more, 603. So 102 multiplied by 2, 402. means 102 multiplied by 2, 204, 541, then I have 5. So I can write 255 is equal to 102 multiplied by 2 plus 51. Again, 0 is missing, so we'll go further. Here, remainder is not equal to 0, therefore using Euclid's division lemma. Now pick 102 and 51. So 102, 51, 51, 2s are 102. If I multiply 51 with 2, that is 102, and we have a 0. So we can write 102 is equal to 51 multiplied by 2 plus 0. I got the 0, so that means HCF of 2, it was 867 and 255 is equal to this thing, that is 51. I hope you got this. So this is Euclid's division method. Using Euclid's division method, we can solve these questions. Very easy, nothing to be worried about. So this finishes our first question. You can make a note of it by pausing the video. I'll go to the next one. Alright guys, so our second question is, show that any positive odd integer is of the form 6q plus 1, 6q plus 3, or 6q plus 5, where q is some integer, right? So this question is very easy. Let's start the question. First of all, before just we go ahead with the question, we should know the meaning of these two words. So first thing is odd. You know the numbers which are not divisible by 2, they are odd integers, and the integers, it's just the counting 0, 1, 2, 3, 4, even in the negative thing, but we are talking about positive, so we are just talking about positive odd integers. So it says show that any positive odd integer. So first of all, I'll say let a be any integer. Mind you, this can be, I said any integer, this can be positive and negative as well, so we'll see later. So first of all, a be any integer. We'll say we know that dividend is equal to divisor into quotient plus remainder. We just used it in our previous question, the question number 1. So this is the same thing. Dividend is equal to divisor into quotient plus remainder. So one thing we need to just see here, we have a 6 here, we have a 6 here, and we have a 6 here as well. So I'll say, for example, if I say, if I'm dividing a, because a is the integer, with this, because I have a 6 everywhere, 6. So what happens? I'll get some quotient, and if I multiply 6 into q is 6q, and I will have a remainder as well. If I divide anything with 6, I will have a quotient and a remainder, right? Now this r, what happens to this r? We will have r's value in this. Why I'm saying this? Because r can be, because if it is multiplied completely, then r can be either 0 or lesser than 6, because if it is 6, then again we can say 6 multiplied by 1 is 6, so it has to be lesser than 6. So the remainder can be either 0, 1, 2, 3, 4, and 5. So these are the possible conditions or possibilities of remainder, right? So now the possibilities are from 0 till 5. So what I can do, I can say a is equal to, so what the equation is, 6q plus 0. If I see here, this becomes 6q plus r, dividend a, if I write it here again, I'll say A is equal to dividend is equal to divisor into quotient plus remainder. You understanding my point? This thing, dividend is A, so I have written A is equal to divisor means 6 into quotient means Q, and R is the remainder. So here A is equal to 6Q plus R can be 0, so I have written 0. Then A can be 6Q plus 1, it can be 6Q plus 2, it can be 6Q plus 3, it can be 6Q plus 4, and it can be 6Q plus 5 also. So these are the possible conditions and the possibilities I can have the value of A. So I'm just moving this side. If I see here, it's A is equal to 6Q plus 0, so I can write it just 6Q. Then I have A is equal to 6Q plus 1. Then I have 6Q plus 2. Then I have 6Q plus 3. Then I have 6Q plus 4. And lastly, I have 6Q plus 5. Okay, so this thing is done. In this one, what I can do, I can take a 2 common. So it becomes 3Q plus 1. In this, I can't do anything. Here also, I can take 2 common, 3Q plus 2. Okay, so what does this mean? It means that here, whatever comes, let the quotient be 1, 2, 3, even or odd. Whatever comes here, if it gets multiplied with 2, it becomes an even thing. So this and this, they will become even. But what is the question? Question is for odd integers. So what I have, even this will be even. Because in case if I want to take 2 out, I can definitely take 2 out. This is 3Q. So whatever is in the bracket, when it gets multiplied with 2, it will be even. So this is also even. So I'm talking about odd. So these are the odds, because whatever I multiply with 6, if the quotient is 1, 2, 3, anything, I multiply with 6 and then add 1 to it, or add 3 to it, or add 5 to it, it will be odd. So that's what our question was: 6Q plus 1, 6Q plus 3, and 6Q plus 4. Therefore, it satisfies the condition and we have odd integers, positive integers, as 6Q plus 1, 6Q plus 3, and 6Q plus 5. So this is what was required. 6Q plus 1, yes, it's there. 6Q plus 3, it's there. 6Q plus 5, it's there, right? So I hope you understood this. I'll just do a small recap of this question. It says, show that any positive odd integer. So I have taken A as an integer. You can write as any positive integer. So I use the same formula, dividend is equal to divisor into quotient plus remainder, and then I saw that 6 is with the q's there, so I took 6 here, q is here, I took the integer as a, and I just did a small calculation. I got the equation that is a is equal to 6q plus r because of this. And then the value of r, it depends on this thing, and it has to be in between this. It cannot go beyond 6. Why? Because we have a 6 here. Whatever is here, the remainder will always be lesser than this. And what is this? This is the divisor. So you need to remember that the remainder will always be lesser than divisor. So what were the things? It was 1, 2, 3, 4, 5, and 6. I just put the value of r in this and I got the answer, right? I hope you understood this. You can pause the video and make a note of it. Alright guys, so now the question number 3. The question number 3, it says an army contingent of 616 members is to march behind an army band of 32 members in a parade. So the first part is there are 616 members and they have to march behind 32 members of the army band. Now, the two groups are to march in the same number of columns. So this is important part, and the two groups, they have to march in the same number of columns. What is the maximum number of columns in which they can march? So the word here is maximum. So whenever you have a word maximum in this type of questions, it means that we are talking about highest common factor, HCF. So first of all, what we will do, I will say, because we don't know the columns, the number of columns, we can say let the number of columns be n. You can put n, x, y, anything, right? Now we have two numbers, number of army contingents 616 and number of army band members. We have 32. Okay, so if I see here this, and one more thing, the two groups have to march in the same number of columns. So whatever the number of columns are, they are, both of them have to follow the same number of columns. So n is same for both, and then I may say that this is x and this is y. Why? Because if I just show you a small figure, if this is the pattern in which they have to accommodate army and the band, then this thing will remain the same, right? This thing I can say x, this thing I can say y, right? So for n number of things, army means n into x, then we have band, that is n into y. What does that mean? If I have to find the HCF, HCF means the common thing, I need to find the n, right? So how to find it? I have two numbers, one is 616 and 32. We will use the same Euclid's division. The first thing, which is the bigger term, 616. So we'll say using Euclid's division lemma, I'll divide 616 with 32. 32 multiplied by 2, it becomes 64, means 32 ones are 32, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So I have 9, this is 5, 3, 2, then I have 6. Now let's see 32 into 5, or 32 into 7 we can try. 7 2s are 14, then we have 21, 22. We'll try one more, 32 into 9. 9, 18, 9 3 are 27, 28. So 9 2s are 18, 9 3 are 27, and then 28. So this is nearer. So I'll put a 9 here, and this is 2, 8, 8. So I have 8 left over. So I can say that 616 is equal to 32 multiplied by 19 plus 8, right? Again, the denominator is not 0, so I'll say remainder is not 0, since remainder is not equal to 0, therefore using Euclid's lemma, again what I have to do, I have to divide 32 with 8, 32, 8, 4, 32. So 32 is equal to 8 multiplied by 4 plus 0. So I have got the 0, so this is n. So therefore I can say n is equal to 8. This is the answer. I hope you understand this. Simple. 616 and 32, we just used the Euclid's division lemma and we got the number. So that is n. Please pause the video and make a note of it. Alright guys, so here comes our question number 4, and the question number 4 says use Euclid's division lemma to show that the square of any positive integer is either of the form 3m or 3m plus 1 for some integer m. Quite a simple question. I'll just start it. I'll say let a be any positive integer. Okay, remember what I did in question number 2? I think that was question number 2. Here I have 3 here and here as well, so I know dividend is equal to divisor into quotient plus remainder, right? This is the same formula. Now if I have a here, if I divide a by 3, it becomes some quotient will be here, 3 multiplied by q, 3q, and then I will have a remainder as well. And if you remember, this remainder cannot be more than this. So what are the possibilities? It can be either equal to 0 or till we have till 1 and 2 as well. So okay, so the possibilities of R can be 0, 1 and 2. Okay, so using this thing, a is equal to 3q plus r. I will just substitute the value of r. So a is 3q plus 0, a is 3q plus 1, a is 3q plus 2, right? This thing can be further modified because we don't use 0, there's no values there. So 3q plus 1, and then we have 3q plus 2. But this was not the question. Our question is we need to see the squares. So now I'll just do the squares of these things. 3q square, it becomes 3 multiplied by 9 q square. Then I have 3q plus 1 square. What does that become? This is a plus b whole square. A square plus b square plus 2ab. That is 9q square plus 1 plus 6q. Now what do I have? I have one more, that is 3q plus 2 whole square. Again, a plus b whole square, a square, b square, 2ab, 9q square, 4 to 6, 12q. Okay, so this is what I got when I'm doing the squares of these 3 things. Now what am I being asked? It is 3m and 3m plus 1. Okay, so here if I write it like this, 3 multiplied by 3q square, no issues. Here if I take 3 common, or before that I'll write one more step so that it will be clear to you. I'll write 9q square plus 6q plus 1. Okay, from these two I will take 3 common. So 3 is common. So what do I have? I have 3q square, then I have 2q plus 1. Here also I'll just write it one more time. Okay, so it is, I'll take 3 common, or I'll do one more thing before this. I'll write 9q square plus 12q plus 3 plus 1. You don't mind me writing this. Why? Because 4 is 3 plus 1. So it's one and the same thing. I'll take 3 common from these 3. 3 is out. 3, 3, q square, 3, 4, q plus 1 plus 1. Right? So now I have this thing, I have this thing, and then I have this thing. Now it says for some integer m. If I put anything here, if the value of q can be anything, so it is an integer. It whole thing becomes an integer, so I can write this as 3m. Here also I can say 3, this thing can be an integer, m plus 1, and here also 3, this thing is an integer, m plus 1. You understanding my point? So these brackets are some integers, because once we will have the value of q, this whole thing will become an integer. Same here and here also. So I have been given that yes, you can put a name that is m to any integer, so I have just given that integer name that is m. So I have 3m and 3m plus 1. That's what was asked, right? You can make a note of it, you can pause the video. Alright guys, so we have the last question of the exercise, that is question number 5. What does it say? It says use Euclid's division lemma to show that the cube of any positive integer is of the form 9m or 9m plus 1 or 9m plus 8, right? So I'll just solve it quickly. So before that, I just want to tell you one small thing. Here we have a 9. So if you remember in my previous questions, whatever was here, we used to get an equation 9q plus r is equal to, I'll just solve it for you so that it will be easier for you. So I'll write let a be any positive integer. Okay, now we know that dividend is equal to divisor into quotient plus remainder. This is the formula that we have been using. Now we have to divide a with 9 because we have a 9 here. So we will have a quotient and we will have a remainder as well. But here, if you see the value or the possibilities of 0, it can lie between 0 and 9. So what does that mean? That you have to take 0, 1, 2, 3, 4, 5, 6, 7 and 8. This is a daunting task. You need to take all these and then you will get these 3 things. But we cannot go this much longer. We have a shortcut for this. So I think you remember that this is the one we have to see, and then these are the possibilities. So we will not do in this way, we will rather choose another way, and that is a shorter way. What I will do, I will say I'll take, instead of 9, I'll take 3 a, then we will have a quotient, then we will have a remainder, or in this case our value for r, the possibilities of r, will be lesser. Now you must be thinking that instead of taking 9, why I am taking 3? If you see, it says use Euclid's division lemma to show that the cube, this is the important part. If I do the cube of 3, it becomes 27. So out of 27, if I want to take 9 as common, I can take 9 as common and I will have the answers. You will see in a bit. So now the possibilities are 0, 1 and 2. So what does this become? This becomes a is equal to 3q plus r. So what are the possibilities? A is equal to 3q plus 0, then 3q plus 1 and 3q plus 2. Remember, that's clear. Now what I have to do, I have to take the cubes. So a cube is equal to 3q cube. It becomes 27q cube. Then I have again 3q plus 1. 3q plus 1 cube. It is a cube plus b cube plus 3a square b plus 3a b square. What does that become? 27q cube plus 1, 3 9q square plus 9q. 27q plus 1, 27q square plus 9q. I can put it in this way as well, 27q plus 27q square plus 9q plus 1. Perfect. Now I have one more, which is 3q plus 2 cube. So it is a cube plus b cube plus 3a square b plus 3a b square. So this is 27q cube, this is 8, then 3, 6, 3, 9, 6, 9, 3, 3, 3, it is 3, then we have 9q square. I can write here 6. Why? Because 3 multiplied by 2 is 6. Then this is 3, 3, 3, 9q plus multiplied by 4. What does this become? It becomes 27q cube plus 54q square plus 36q, and then this 8. Okay, so now what is required? I have to have 9m. So I can do one thing here. I'll put 9 3q cube here. Then what is required? 9m plus 1. So if I take 9 common from these three, I'll write it here. 9, it becomes 3q cube plus 3q square plus 3q, and then plus 1. And this thing, I'll take 9 again common, 3q cube plus 9, 9 for 9, 6q square plus 9, 4q plus 8. Right? Now, what was the other thing? It says, using Euclid's division lemma to show that the cube of any positive integer is of the form 9m, 9m plus 1, and 9m plus 8. So this thing can be an integer. I can write this as 9m. This thing will be 9m plus 1, and this thing will become 9m plus 8. Okay, so even though we did the question with 3, we still got 9. Why? Because it was cube. So we can get it by this formula as well, by this method as well. So this finishes question number 5, and this finishes your exercise as well. You can just pause the video and make a note of it. And this is one of the important questions of this particular exercise. I hope you understood the chapter, the exercise. In case if you have any doubts, you can just comment down below, and please do subscribe to Posh Coaching Classes, because I will be bringing a lot of stuff on this subject and many more subjects to come as well. You will have all the exercises, solved on this channel. So please do subscribe to this channel. This is me signing off for today. You have a great time. Please stay in and please stay safe. Thank you so much.